Welcome back. In our last lesson, we learned to identify overfitting and underfitting. Today, we're going to dive one level deeper and understand the theoretical reason for these problems, the famous bias-variance trade-off. Any machine learning model's total error can be broken down into three parts. There's irreducible error, which is the random noise we can never get rid of. But the two parts we can influence are bias and variance. The best analogy is an archer. Bias is their systematic error, how far their average shot is from the bullseye. Variance is their consistency, how spread out their shots are, regardless of the average. First, let's talk about bias. Bias is error that comes from a model being too simple. Its assumptions are too strong, and it fails to capture the true, complex relationship in the data. A model with high bias pays too little attention to the data, and this leads directly to underfitting. Now for variance. Variance is the error that comes from a model being too complex. It's so flexible that it becomes overly sensitive to the training data, learning not just the important patterns, but also the random noise. A model with high variance is unstable, and this leads directly to overfitting. This leads to the crucial trade-off. As we increase a model's complexity, its bias tends to go down. But at the same time, its variance starts to go up. We can't minimize both at the same time. Our goal is to find the sweet spot in the middle, that level of complexity where the total error, the sum of bias squared and variance, is at its lowest possible point. So, let's put it all together. A simple model has high bias and low variance, which results in underfitting. A very complex model has low bias but high variance, which results in overfitting. The just right Goldilocks model is the one that finds the optimal balance between the two, minimizing the total error. And that's it. The bias-variance trade-off is one of the most important theoretical concepts in all of machine learning. It gives you a mental model for why you must always balance model complexity. Now that we have this theory, let's move on to our first practical algorithm. In our next lesson, we will explore linear regression.